Hello, ladies and gentlemen. Welcome to Chapter 2 of Small Hydro Technologies program being run on the University of Science and Technology. Chapter 2 deals with the classification and definition of small hydro schemes, the various stages involved in the design of a hydropower scheme, as well as cost-benefit analysis. The learning objectives among others includes identifying the components of a hydropower scheme and use formula presented to calculate power from falling water. Describe the stages involved in the design of a hydro scheme and calculate power factor and unit energy cost. Classification and definitions of hydropower schemes. Hydropower dams are usually classified into three levels as full scale, small or mini, micro or pico hydro schemes. For large hydro schemes, normally the projects range from 100 megawatts and above, which fits into national grid. For medium hydropower plants, the projects run from 50 megawatts to 100 megawatts and also feed into national grids. Small and mini hydro dams range between 100 kilowatts to 15 megawatts. They also can feed into national grid, as we call them standalone systems. Micro hydro dams and pico hydro dams ranges from 5 kilowatts to about 100 kilowatts. They usually provide power for small communities or rural industry in remote areas away from the national grid. Types of hydro systems. We have the impoundment hydro dams, run-of-the-river systems or diversion hydro dams, then the pump storage hydro dams. This slide shows a typical conventional impoundment dam, where we have the dam itself, either built as an embankment dam or a gravity dam. Then we have the water stored behind the dam, and then the penstocks, the powerhouse, and then the transmission lines extending the power generated to the national grid. An example is the Hoover Dam in the USA and the Akosombo Dam in Ghana. Diversion or run-of-the-river hydropower schemes. In the diversion or the run-of-the-river hydropower schemes, we make use of a stream and elevations as a result of a mountainous area. A weir is introduced in the stream at the top, and a penstock is connected to a small powerhouse at the tailways to generate power. The water lays down into the tailways to drain the river downstream. This is a typical example of a run-of-the-river hydro scheme. Pump storage schemes. To be able to have a pump storage schemes, you need to have available power generation system in the generation mix. For example, you need to have a nuclear power plant that will be doing base loading. And you also need to have differences in your energy needs as off-peak and the peak demand periods, such that at the off-peak periods, your hydropower plants will be used as reversible pumps to pump water from the tailways back into the reservoir. And then at the peak periods, the reservoir serves as enough energy to produce power back into the system. Example is the Colorado Dam in the USA. This slide shows typical arrangements for small hydro schemes. As I said, you have a river or a stream flowing, and then you provide a weir to dam it upstream. You connect the weir through channels to the forebay. A forebay is basically a tank that stores water for daily usage. And then you connect the penstocks to the 4-bay to the powerhouse. We also have the dam toe base storage schemes. And then we have the canal 4-bay schemes that give the opportunity of tapping water through the canal for power generation. This slide basically shows the various components of micro hydro scheme, where we have the river system, and then we create a weir, connect the weir through a channel to the 4-bay, as previously said, then connect penstocks to the 4-bay to the powerhouse, generates electricity, and water goes down to the downstream out of the river. Now let's look at the technologies for small hydro projects. Head. The head is the difference between elevation from a high elevation to a lower one. The water levels in the 4-bay, for example, is the water levels in the 4-bay and in the 10-bay. This is called the head. It's usually measured in meters. Based on the head, you have 3 categories of dam. You have the high head, which ranges about 800 feet or close to about 300 meters and above. Medium head ranges from 100 to 800 feet, that's at 300 meters. And a low head, less than 30 meters. Hydropower is very efficient. Efficiency is derived from the electrical power delivered to the bypass divided by potential energy to headwater. As any energy conversion system, there are typical losses due to frictional drag and turbulence of flow, frictional magnetic losses in the turbine, generator, and in the whole power system. Overall efficiencies range from 75 to 95%. The power equation. The power equation is given as gravitational acceleration times the efficiencies of the power system times the flow rate times the head. It's always as it's given in, the power is given in kilowatt if the gravitational acceleration is in meters per second squared, and the discharge is given in meters cubed per second, and the head in meters. We also want to talk about other terminologies on the Planck factor, sometimes also called the capacity factor. The Planck factor is basically the power used times the time of power used divided by the power installed times the time under consideration. It's also equivalent to energy used divided by energy available. Load factor, as Planck factor, is defined as the total energy used by customers hooked onto the network divided by total energy capacity connected to customers. It can also be described as total energy consumed during a period over the maximum installed capacity times the hours in that particular period. Unit energy cost is defined as the total annual cost, including operation and maintenance costs, divided by energy consumed usually per year. It can also be defined as the total annual cost divided by power used and the period for which the power was used. Designing a hydro scheme. To design a hydro scheme, the following stages have to be undertaken. 1. Capacity and demand survey study. This survey forms the basis of a financial study. It establishes accurately how much energy is wanted for what purposes, when it is wanted, and where it is wanted, and users of the scheme. 2. Hydrological study and site investigation. This establishes the hydro power potential of the site. It shows how much power will be available and when it will be available. 3. Pre-feasibility study. This is usually a quick cost study of a range of design options and rural energy sources. The hydro scheme will usually identify 3 or 4 different approaches to satisfying the customer demand. 4. Feasibility study. If discussions following the pre-feasibility studies indicate that one of the scheme is viable, then we proceed to detailed design engineering calculations and costing. It is important not to omit the full operation and maintenance costs.